Hello everyone, Sahil here. Today we will learn about PCA, Principal Component Analysis. It is by far the most widely used dimensionality reduction algorithm, and it is by far the most popular dimensionality reduction algorithm. It's really interesting, it's really exciting, and you will really like the concept. So let's just jump right in. So let me just give you a brief overview of PCA. So as I told you earlier that machine learning can be segregated into three parts or maybe four parts: supervised learning, unsupervised learning, self-supervised learning is another part, reinforcement learning is also there. So PCA is an unsupervised learning algorithm. So unsupervised learning consists of clustering algorithms, association rules, and dimensionality reduction. So what is dimensionality reduction? Dimensionality reduction, as the name suggests, we are reducing the dimensions, we are reducing the features. That's why it is an unsupervised learning algorithm, because it is all about the features. It is the X. The labels aren't used. The labels don't really matter. They aren't used in the training process. So in PCA, it is all about the features, and it is all about reducing those features, reducing those dimensions. And how do we reduce those dimensions? Let's say that you have many features. You have a lot of features, and you have like hundred or thousands of features. You cannot look at every feature and decide whether it is important or not. But these features are taking a lot of space. They are taking a lot of computation to train. Now you want to reduce these features. Now, how do you reduce them? You remove the features which don't really matter. You remove the features which are not really contributing to the training process. They don't have much value. But when you have thousands of features, you cannot really decide, you cannot make a decision. And PCA is used for that. Another way of saying this, another way of saying dimensionality reduction can be that we are finding principal components. Principal are the main components, the components that really matter. So let me just explain you the intuition behind PCA in the next slide. So let me just explain you PCA with the help of this example. Let's say that you are asking me what should I wear for a wedding, and I start explaining to you that, you know what, a long sleeve shirt would really suit you, and you should also add a tie to that, and wear some nice trousers, take some nice shoes, wear a nice belt, and also wear a jacket over that. And then you will just tell me that, why didn't you just tell me that I should wear formals, that I should wear a formal suit? Why are you explaining me the same thing with so much more information? That's exactly what PCA does. PCA is combining the features, combining the value in those features, representing the variance in those features in a short way. Combining those features, reducing that information, and giving it to you in a short form. That form doesn't really lose the information. As I told you earlier, that you should just wear the formal suit. I didn't exclude any information. Well, you might say that the picture I have shown you here, the guy is also wearing a watch, and I didn't tell you about that watch. Well, that's exactly what you lose. You lose like 5 or 6 or 10%. And you can decide that. You can decide how much you want to lose and how much you don't want to lose. So let me just explain you with one more example. Let's say that you want to assess colleges for your admission. You want to join into some course, and you are checking out these colleges, checking out these universities, and you are trying to make a decision. And you are looking at the infrastructure, you are looking at the number of labs, you are looking at the number of professors, what are their qualifications, what are their reviews, what is the location of that college, what are the number of courses offered there, what is the quality of those courses, what is the fees, how is the accommodation, etc. Now this is too many features, this is too much information, it is taking too much space, it is taking too much computation on your part, and it is just becoming difficult for you to make a decision. So why don't you just look at the placements? Just look at the placements of that college. Just look how many people graduating from that college are actually becoming successful, are actually getting the jobs that they wanted. Now, this is just one feature. The other features, which started from infrastructure, the professors, the quality of courses, fees, accommodation, this was too much information. Now, you are representing the same information because that information really contributes to the student's success. You are combining that information into one feature. All of those features now are converted into this one feature called placements. Now it is easily understandable, it is a better representation, it takes less space, it is good for your computation part. This is what PCA does. PCA takes these features and combines it in a way without losing too much information, which takes less space, and in short, it really just takes the principal components. It really takes the components of your dataset, components of your features that really matter, that are really important. And you won't realize that many times when you are working on datasets, many times when you are working on different problems, you will see, or you may not notice this, but it really happens a lot. There are a lot of redundant features. Those features, because these are real life situations, many features are actually correlated with one another. They are not independent of each other, they are correlated with one another, and they do depend on one another. And that's why PCA can actually combine those features in a way and represent in a short form, which can really help you. Now let me just explain you that again. Let's say that you have two features, x1 and x2. And if you take these two features and you compare them and you make a graph of that, you can see the graph of that right here. Now what do you see? You have these points and they do seem to lie on one line. Now think about it. Why do we have to store x1 and x2? Why do we have to store these two separate features when we can just approximate them on this line? This solid line, you can see that there are three lines. One is the solid line, the other is a dotted line, and one is a dashed line. The dotted line doesn't represent these features at all because it is perpendicular to the solid line. The solid line is the line which can approximate x1 and x2 while preserving the most of the variance. Another way of saying it is that when you approximate x1 and x2 on this line, you are losing the least amount of information. PCA does this. PCA finds this line for you and it generates a new feature. And this feature is correlating x1 and x2 into 1. Now, two dimensions are converted into one dimension. And this is just one principal component. Let's say that you have 1000 features. You can use 100 principal components or maybe 50 principal components, and you won't really believe it, but in real life situations you can actually reduce the number of dimensions on that level. You can reduce the 1000 dimensions into 100 dimensions and still you can retain the variance, still you can retain the information, still you can get away with that without losing a lot of information. Now this is really cool because 1000 features and 100 features, it is a big gap, it is a big difference. There is another example that you can see here where we have three dimensions, x1, x2 and x3. Now if you see these features, if you see these points, you will realize that this they do seem to lie on one plane. So why do we have to store these three features when we can convert them into two features? When we can project them onto this plane, and that plane will help us approximate these features. That plane preserves the most amount of variance. That plane retains the most amount of information. That plane loses the least amount of information. Now, how do we do this? Basically, to find this solid line or to find this plane, we use singular value decomposition, SVD. Now, what is SVD? SVD, singular value decomposition, is a standard matrix factorization technique, and it gives you basically the eigenvectors. The eigenvectors u, s, and v. Now you might say, what is that sigma there? What does it mean? That sigma is called the covariance matrix. And how do you compute this covariance matrix? Well, I have written the formula for you. You just have to take the feature, you just have to take the example, and you have to take the transpose of that training example, and you have to multiply that. And there you have the covariance matrix. Now, this advanced mathematics, these calculations, how do they actually find the solid line? How do they actually find the plane? How do they actually find the principal component? It is proved actually, and the mathematical concept is really complicated. And understanding that concept wouldn't really necessarily help you implement PCA. So, we are just going to implement the results. We are going to take the results, and I will tell you how you can implement PCA for your own problems. Now, let's just start with the steps. What are the steps that you need to implement PCA? Now, to train for PCA and to predict using PCA, there are different set of steps. Let us just start with the training part. So, first of all, to implement PCA, because it is an unsupervised learning problem, you are only dealing with the features. You are only dealing with the dimensions. The labels aren't included here. Now, when you have these features, these dimensions, the first step for you to do is that you have to implement feature scaling. Feature scaling becomes really important because to find those solid lines, to find those planes, or to find those number of principal components, if you implement feature scaling, it really helps. Otherwise, the task becomes really difficult. It becomes really difficult. And why do we have to do that? Just implement feature scaling, and it just smooth it out the data. It just helps the learning process. So you implement feature scaling. The second step, as I told you earlier, for every training example, you have to compute the covariance matrix. Now that's easy. You just have to take the transpose and you just have to multiply. Now, when you have this covariance matrix, you implement SVD, singular value decomposition. Now there are many libraries, even NumPy has that, sklearn has that. Just give it the covariance matrix and it will give you the eigenvectors u, s, and v. Now that's all. That is the training part. Now to predict. Now what we are predicting here, there are no labels. We are converting x to z. Now x is n dimensional. Here will be like 1000, 100. But you are converting those many number of dimensions into less number of dimensions. So k will be less than n. K will always be less than n because you are doing reduction, you are reducing the dimensions. Now to do that, let's say that you want k number of dimensions. You had n number of dimensions, k is less than n. You want k number of dimensions, you want to reduce from n to k. Now what do? When you compute these eigenvectors, you take the first k columns of u. That's all. That's your new training example. That's your training example which has the information, but it has only k features. The earlier one had n features. This one has k features. The dimensionality is reduced. That's all you have to do. Now that's really easy. The mathematical concept is really complicated, but the implementation part, it's not that difficult, and it's a really powerful algorithm. Now let us just get into more details. The basic technical details that you need to know, the basic things that you need to know in order to implement PCA. Let's get into that now. Now, the optimization objective. I think you can guess it. When we have these two features, you can see this graph, we have these two features x1 and x2, and we are trying to get one feature out of that. We are trying to combine these two into one. So basically we are trying to find that line, and you can see that this line retains the most amount of variance, but still we lose some information. You can see that there are some outliers, there are some points which are far away from this line as compared to others. Now this distance is what we are trying to minimize. We are trying to minimize this distance for every training example, because we are approximating this new feature, we are approximating the value of x1 and x2 so that we can combine them into one. When we approximate them, we are basically projecting them on this line, and we try to project them on a line where the projection error is the least. Now this distance, this difference between x and the projected x, this is what we are trying to reduce. Now for the feature vector x1, we compute the approximated value of x1. The approximated value basically lies on that line. For x2, we compute the approximate value of that, and that approximated value is on that line, and we try to minimize the difference between the approximated value and the real value so that we don't lose a lot of information. This is the optimization objective. This is what we are trying to minimize. This is like a cost function, because when this is minimized, when we have the least value of this, we have the best lines, we have the best planes, or in general we can say we have the best principal components. Now you might be thinking that, let's say I have 1000 features and I am trying to reduce that amount of information into less number of features. Now, how do I know what is the right amount of principal components, what is the right value of k for my specific data set? Because that will depend on your data set. You don't have to go with your guts. You don't have to take the value of k that you feel like it. This is not the right way. The thing that actually matters when you are choosing k, the thing that actually matters when you are choosing, when you are trying to figure out the number of principal components, is the variance. Because the variance contains the information. The variance that you are capturing, it really matters. And the value of k, different value of k's will have different values of variance. And let's say that you retain 99% of the variance, which means that you only lose 1% of the information. It's really good. Now you will get that result with a specific value of k. Different values of k will give you different values of variance. If you will go to the extremes, of course the variance retained will get reduced, because you have to store that information in some way. If you reduce k too much, you will lose that. Now how do we know that? You can just use this formula which I have written here, and if it's less than 0.01, it means that you have retained the 99% of variance. What is the recommended percentage of variance that you should retain? I would say you should never get below 85% or 90%. Never go beyond that, because you will lose information and you will not get the results because you lost information. Now you might think that this is a really complicated formula. How will I do that? Well, there's an easy way. The eigenvectors you computed, there was also an eigenvector there named S. You can just use that S in the formula given below, and you can calculate the amount of variance retained. If the variance retained is above 90%, you can choose that value of k. That's all. It's that easy. Now you might be wondering that you had n-dimensional features, you implemented PCA, and you got new features. You got k-dimensional features. Now, is there any way that you can go back? Is there any way that you can generate your previous features which were n-dimensional from these k-dimensional features? Well, yes, you can do that, but not exactly. Well, remember that you were using the approximated value of x, because that is the value of x which you use to combine and generate this new feature z. That approximated value was used in generating these new features. Well, you can just use the transpose of the U matrix and you can get the approximated value back. But there is no way that you can go from the approximated value to the real value because you lost that information. And the difference between the approximated value and the real value, we use that to compute our variance. So let's say that you retain 90% of the variance. So yes, you can get your data back. But the data you will get back, it will lose 10% of the information that you already had. So this is the way that you can actually get your data back. You cannot totally get your data back because you lost something. You lost some amount of variance. Because you reduce something, you have to give something to that too. Now let me just show you how you can implement PCA using sklearn library. So you just import the PCA object from sklearn library and you just select the number of components. The number of components is the new number of dimensions you have. So you can have any number of dimensions. So here we gave it 2. Now you just have to call the fit transform function on your dataset, on your features, that is the X part, and it will just generate the two-dimensional features for you. It's that easy. Now remember that I told you that you have to implement feature scaling. Now this sklearn library, it implements the feature scaling part by itself. So don't forget that. If you are using some other library, don't forget that part. This library implements the feature scaling itself. Now remember I told you that different values of k will give you different values of variance retained. Now you are choosing the value of k, and just like in KNN or k-means, you were using the elbow method with the trial and error method to get the best value of k. You can do that here also, but you can also use the sklearn's library functions to get the value of k for specific variance you want. So in this case, you don't tell it the value of k, you just instantiate your PCA object and you fit that PCA object on your features, that is your x. And then you call the come_sum function and you just tell it the PCA dot explained variance ratio and you tell it the value that you want. So if you tell it that I want 0.95, that is more than 95% of variance or equal to that, so it means that not anything less than that, it will give you D. And D is the value of components, D is the number of components that will give you that. So it is an easy method. You can also use the elbow method, both are fine, and you will get the same value of K for the specific variance retained. So let me show you an example where you try to get your data back. That is, you are trying to reconstruct your data back. So I am showing you the MNIST example. MNIST is a data set of integers, their images, and the amount of features for each example in this case was 784. So you run PCA, you implement PCA, and we are converting those 784 features into 154 features. So this is a huge difference. 784 to 154, this is a huge difference. And we implement PCA and we get our reduced dimensions. We get our new training examples with only 154 features. And we use the inverse transform function to get our data back. And then we visualize it. Now let's compare that. You can see the original one and the compressed one. This is the fantastic thing about PCA. You reduce 784 features to 154 features. still you can retain most of the information. It combined most of those features into 154 features. We didn't just delete the features, we combined them into one. We combined the 784 features and we made those combinations. We calculated the best combination and we got them in 154 features. We have that information in 154 features. And the variance lost because you lost some amount of information, obviously. The difference is the lost variance. And you can see it doesn't really matter. You retained most of the information. That's why PCA is one of the most popular dimensionality reduction algorithms because it is so efficient and it works so good because you had 784 features, now you only have 154 features, and you can totally use this new reduced dimensions. You can totally use these new time training examples and you will get the good results. And it is really beneficial because your space complexity is reduced, your computation is reduced, and it just speeds up your process. Now, if you have studied linear regression, you might be thinking that PCA and linear regression, they both look really similar. They look similar, they seem similar, but that's the only part. They just look similar. They are totally different algorithms. One is a supervised learning algorithm where you are trying to predict a numerical output. The other one is an unsupervised learning algorithm where you are trying to reduce the number of dimensions of your training examples. The training process is different, the results you get are different, they just look similar. And let me just discuss the part that looks similar because even that is different. So, in linear regression, you can see that you have basically the similar part is that you are trying to get that line, you are trying to predict that line. But the difference is that in linear regression, you are trying to use that line. You are you are using that line, you are learning that line, you are learning the function that defines that line so that you can use that line to predict. You will just give it the features and you will just get that point on that line to get your label. You are using that line to predict labels. And the difference of y, the real value of y and the point on that line, that difference is the error that you are trying to minimize. And you can also see that in the graph shown. In PCA, what you are doing is there is no label y, but still you are trying to predict that line. Yes, you are trying to predict that line, but you are not using that line to predict labels. You are using that line to project your training examples, to approximate your training examples, to approximate your features on that line. And that line or that plane or whatever is the region where that projection error is minimized. You are trying to project your features onto this line. The line doesn't really matter. The new features generated, they matter. You are trying to get new features out of that because you are minimizing the number of dimensions. The number of features is reduced. You are trying to use the surface of that line or the surface of that plane, the surface of that region to get these new training examples, to project them. You are not using the line to predict new labels. So these are totally different algorithms. They look kind of similar, but no, they are totally different. Now, there are some things that you need to keep in your mind when you are using PCA, when you are implementing PCA. These things really matter and they do affect your results. So, the first thing is that you should always implement feature scaling. You should always scale your features. In PCA, it becomes really important. Even in other algorithms, feature scaling really helps because the learning curve, when you are minimizing the error, if your features are scaled, it really helps the algorithm. It smooths out the process. The other thing is that when you are trying to choose the number of components, that is k, you should not just go with your guts. You should decide the amount of variance you want to retain and then get the value of k. and then use that value of k. And the last thing is that just like any other algorithm, use your training set for the training, the validation set for the validation part, for the hyperparameter tuning part, and the test set for the testing part. So in PCA, what is the training part? The training part is generating that mapping. So when you are generating that mapping, when you are using those eigenvectors, but when you have your examples from validation set or test set, you don't generate a new mapping for that. Use the same mapping. Use the same mechanism that you learned for your training set. Now there are some unwise practices. So as you know that PCA can actually reduce the amount of features. Now what happens is that sometimes when you have too many features, or in other way I can say that when you have less number of training examples, you end up overfitting. Instead of trying to counter that problem, people implement PCA and they try to reduce the amount of features so that they can address the overfitting problem. So this is not recommended. You may get the results you want, you may not get the results you want, but this is not generally recommended. I would recommend that you use regularization instead, because your problem is overfitting. PCA addresses a different problem. You have too many features, but you want to retain that information. And also, when you have a problem of overfitting, the labels are also included, and PCA just doesn't think about the labels. But regularization, it does account for the labels. So regularization and other overfitting techniques, they are the solution for overfitting. PCA is not a solution for overfitting. So don't try to use PCA to counter overfitting. The other thing is that let's say that you are working on a project and you are just starting out. So you take these features, you take the data set from somewhere, or you make your own data set. Instead of actually using that data set to get the results, some people implement PCA on that and try to reduce the number of features. But the thing is that why don't you just try with the original data set first? Maybe you just don't need PCA and it is just a distraction. So try to implement what you have first and then see whether you need PCA or not. Applications of PCA. I think you already have an idea about them. Now let's think about what is the task that PCA does for us. PCA takes highly dimensional features. When you have many features, a lot of features, it takes those features and it gets the information out of them. It represents the information out of them with less amounts of features. It retains the information, but the number of features are reduced. Why? Because in real life situations, the features are often correlated. Let me give you an example. Let's say that you are a tall guy. Now, because you are tall, because your height is more, your weight will also be more. Now, your height and weight, these are correlated features, these are not independent. And in real life situations, because the features are always interconnected, they are always correlated, we can find a way to represent those features in a short form with less amounts of features. And when you have less amounts of features, the amount of memory needed to store those features is also reduced. When you have less amounts of features, the amount of computational resources needed to train on the dataset is also reduced because now you have less features. The last part, which is really interesting, that PCA can help you do, let's say that you have 50 dimensional dataset. You have 50 dimensions. Now you cannot visualize that because we can only visualize one dimension, two dimension, at most three dimensions. We cannot visualize anything which is four dimensional. We cannot visualize anything which is five dimensional. Now to visualize that, you can of course take those features and tell PCA to get two components out of that, to find two principal components. Now, of course, this will have an effect on the variance. But remember, retaining the information and training on that dataset is not the goal. Your goal is to visualize the dataset, to get an idea about the dataset. And you can implement that. People use that, and it's really useful. The variance is not 90% obtained, it's the value is not high. The amount of variance retained gets reduced because the number of components are reduced. But when it comes to visualization, PCA is often used. And the fact that information is lost, some amount of information is lost, but still you can get an idea about the data set, which you wouldn't have gotten when you had 50 dimensions.